Okay, well, I'd like to introduce our next speaker. I can do your first name, Ravi, and I'll mainly go ask him. Gagna? Gogna. Okay. Sorry about that.
That works.
Okay. And he comes to us from NASA, and he's going to talk about some field robotics.
Yeah. I think
Let's welcome our speakers. Hey, guys. People need the T-mic back there. T-mic. Cool. Good. We got it.
All right, everybody, thanks for having me down here. I'm Ravi. I work at NASA Ames over here. Let me get some logistics stuff out of the way real quick. I work under the ISRDS-2 contract under SGT, and anything I say here does not represent the opinions or comments of NASA or SGT. Now I can say what I want. So, I came here in contact with Alan, who was my boss, Terry Fong, which leads our group, Intelligent Robotics Group, just a little bit down the road here at NASA Ames. So I'm here to talk a bit about our project we had last summer. We had a project called Surface Telerobotics, where we had astronauts teleoperate a robot here on Earth. So I'm going to talk a bit about exactly how we define telerobotics, what that means to us, how we implemented it, and then I'm going to discuss a bit about the robot itself, what kind of sensors we have, what kind of software we use, given the population of this group. I think that would be interesting. And we just got a new robot called KREX-2, which some may have seen at the last robotic or block party we had. I was the one kind of driving that around. So I'll talk a bit about that, and we're going to use that in our next few missions here. So a bit about our motivation. So I'm getting back to the first topic here is on surface telerobotics. So the mission here is to have robots that can be teleoperated from a spacecraft or some other orbital mechanism that we're going to have to use. Some missions that we have are the Lunar Farside mission. So this is using the Orion spacecraft, placed in the Lagrange point on the far side of the moon. And it will be stationary there and control a robot that we put on the moon surface itself. And this is leading ourselves out into deeper space. So as we move further, the next step is a near-Earth asteroid. Similar thing, we want to teleoperate a robot on the asteroid itself. And from there, the ultimate mission is to get to a Mars orbit and be in orbit around Mars and control a robot that's on the surface of Mars there. So in the development of these plans, different people higher up than me and NASA have come up with certain assumptions and certain gaps in technology. So what we want to do is know if those assumptions are true and how do we start bridging those gaps into technology. So that's what we've been working on here for the past year. So last year we began this testing with the ISS. So let me define here what do we mean by telepresence? So the Human Robotic Partnership is a society that develops a paper. And in that paper, they define telepresence, which is what we kind of stand by. So teleoperation of a robot acted on a planetary surface by a person who is relatively close to the planetary surface. So that relates back to us having something in orbit around the planet, and we're controlling the rover on that surface. And this is a roadmap we developed. So before I started with the group, they did a lot of ground analogs. Developing the telerobotic system, working on the autonomy and data concern, what type of interfaces do we want, implementing the different tests for the ConOps, how we're going to operate the system in the field itself. And the next step is to integrate with the ISS laboratory. The closest analog to us that we have here is to use the ISS as our space capsule. And now we're the planetary surface. So all the infrastructure is already in place. That's a great use case for us to use it and test our system. So with this, we want to obtain engineering and op data. We want to validate what we've done on the ground analogs itself, and we want to reduce the risk as we move further beyond this point. So this is, in my mind, the last point of testing before we go to a real full-fledged mission. there, like we talked about, go to lunar orbit and Mars orbit from there. So some key points that we want to have. You want to know the crew control. They're going to be the one controlling the robot, and they're going to be controlling from ISS. So what type of interfaces do we need? What type of GUI interaction do we need? There's a whole other realm of how do you deal with all the logistics on getting stuff on ISS, which I won't delve into because it's boring as hell. The human robotic ConOps. How do you integrate with a human robotic ConOps? So let's be clear that we're not making our goal is not to make a fully autonomous robot. We want to have something that's semi-autonomous. We want the robot to be able to handle the low-level controls that are tedious and unnecessary for a human to have to interact with. Yet there's some scenarios where we do want to have human interaction. So trying to find that threshold is a difficult choice to make, and that's something we want to develop along this path that we've taken. And as we have this mission, it's very important for us to pre-plan what type of metrics we want to gather from this, right? If we just have tests and it goes and fails or succeeds, we don't have metrics, we don't have to proceed from this. So we have a group that's well-defined the metrics we want to use, and that includes the robot use case, the crew use case, data communication, tasks, and so forth. So implementation, how do we do this? We do this using we're doing this simulating the lunar Lagrange point mission that I discussed earlier. And we're going to use this with the ISS in the United States Orbital Station. So that's something our PR put in there. The K-10 rover in NASA Ames RoverScape. So I don't know if anybody has seen the K-10 rover. It's been on a little bit of media. We have these tests going on. It's a smaller version of the K-Rex that we had at the block party. That's the robot that was used in this test. You'll see some pictures as we go through these. And so through this ISS testing, we had 3 astronauts control it, and in 3 different phases that we had in the mission. So we had Chris Cassidy, Luca Parmartino, and Karen Nyberg on these different dates last summer.
Question?
Yeah.
It mentions a telescope proxy. What's that about?
Yeah, so I will get into that. We have the lunar far side mission. Let me delve into that a little bit more. So the lunar far side mission, the goal is to get on the lunar far side, which is always facing away from Earth, so we don't diminish its ability to pick up radio frequencies that are out in deep space. So what we want to do is we want to lay out, the goal is to lay an antenna out, antenna proxy, or on the lunar it'll be a real antenna, on Earth we do an antenna proxy. And that will allow us to hopefully get some more information on our cosmic con. And we have audio on here?
Yeah, it should come through the HDMI.
Tried doing it earlier.
You tried it on this? It should come through here.
Give it a shot. No. It's still on here.
Space lights. Turn it up loud.
Well, let me mute this and I'll just kind of talk through. So this is showing the video of our mission that we had last summer. So this is the RoverScape that we have at Ames. And we have the rover here driving. Let's restart that. We have the rover driving that, and in this case, the rover is being controlled by Luca Parmartino. This is the picture of him in the space station itself. So he's using an ISS computer on board that we've sent our graphical interface to. So he sends the commands at different stages, and the robot will execute what he requests here on Earth. Please go ahead and let's, make this interactive. If you guys got questions or something, throw them my way. So this is kind of getting a hand up. Oh?
Yeah, that gives a hand up.
Yeah.
What's the delay time from the space station to the robot?
So it's about half a second going through the different gaps that we have. And if we were to control a robot directly on the far side of the moon, it'd be about 3.5 seconds, given we had some type of satellite to relay the image on the far side.
kind of data rate are you guys expecting to be able to get back and forth?
So we limit ourselves to 1 megabit per second is where we want to have. In this test, we went up to about 1.2 was kind of our high side. So we're close to what we think would be a realistic data. And we put a lot of effort into that in the different APIs that we set up and how do we control that. So this is just a bit about the mission here. The lunar far side of Lagrange L2 is the Lagrange point number 2. And robotic ConOps, I kind of went over this a bit. The orbit might be a bit hard to see, but if anybody's not familiar quite with the Lagrange points, you have this is the Earth, and this is the Moon. These are the paths that we're predicting that the spacecraft would take for a setup here. So you have the Earth, the Moon. Obviously, the back side of the Moon is going to be the far side, and we're going to put the spacecrafts in the Lagrange point here. So L2 is the Lagrange point. There's different ways about to halo yourself around those different Lagrange points.
So you're using an unstable Lagrange point because that's the only one that has a clear view of the far side of the Moon or something?
Right, yeah. Any other hands up? Yeah.
So you're using telecommunication for the far side of the moon. How are you balancing or how are you communicating with the robot on the far side? Is there an antenna on the moon that will communicate with it? Or how are you balancing the signals?
So if we have a mission on the far side of the Moon, we'd have a spacecraft on the far side, and then we'd have a rover on the Moon itself. So there would be no communication directly back to Earth in that use case. Is that your question?
Yeah.
Okay. And to mimic that, we've done it here on Earth, where we have ISS is orbiting here on Earth, and we're controlling a robot here. Yeah.
So my naive point of view would be that the moon would block the signal to the ground satellites?
So,
No.
if we have a spacecraft at the Lagrange 2 point,
Right.
and the Moon's in the center, that's going to block us Earth. But the use case here is that everything can be done independently of communication from Earth
Okay,
to a certain extent, right?
Because the spacecraft is near.
The spacecraft will have direct communication with the robot, and there's other ways of for that use case itself is independent,
Okay.
right? And then from there we can relay data back to the Earth.
Is this halo orbit in the plane of the Earth and the Moon, or does it go above and below that?
That's beyond my scope of knowledge.
Oh,
Yeah,
okay.
sorry.
Because if you could go above and below it, then you wouldn't have a problem with being invisible from the Earth.
Right. I mean, in reading the project plans briefly, there's points in the halo orbit where we can relay data back to the Earth and back to the Mission Control Center. So,
Just a question however big the halo happens to be.
right. So some of these videos are kind of boring to watch without audio, but this is, the K10 rover roaming around. And sorry, what's that?
You can almost hear it.
Okay.
Either if you're on the surface, you're wanting to move from Mars, or from this K10 rover is whose LiDAR is that?
It's a Velodyne 32 laser LiDAR.
Cheap one,
It's expensive, but it's the cheap one, yeah. So the way we've split up this first mission, we split up in different phases. So the goal is for the astronaut to control the rover, and in that scenario, there's 3 phases that we split it up into. The first phase is to survey the land, survey where do we want to put the antenna, and check it out. The second phase is actually deploying the antenna. So the robot's equipped with the roller itself, and antenna rolled up on it to go and deploy the antenna out in the landscape that's defined in the surveying phase. And the third phase is the telescope inspection. So once the antenna is completely laid out, the rover will go back and take panoramic pictures of the area and allow the astronaut to, assure that those telescopes have been laid out in a fashion that they're satisfied with. And the way we did it, because we have limited time with the astronauts, is we had 3 sessions with the astronauts themselves. So we split up the astronauts into primarily focusing in one phase independently. And this kind of talks to the data rate I got a question about. So this kind of is not the normal use case for that ISS is kind of used to. They're used to the case where they're doing an experiment or a study on board, and we want a lot of data. So the majority of the data is coming down to Earth. Here it's kind of the opposite, where we want a very limited data because of the nature of the robot. The robot itself is semi-autonomous. So the kinds of commands that need to be sent to it are higher level commands, and therefore hopefully less frequent, and therefore less data. So that's kind of shown here in the graph, or in the data layout. We have the downlink from the ISS computer there, and it's coming down through the rover through a network configuration. And the average speed throughout our test are about 2 kilobits per second. And we say here 1 second delay max. On average, we're seeing about half a second. And on the upload side, so we have the robot that has all the sensors on board. We want to give the astronaut some situational awareness of where it is, what the landscape's like, what type of obstacles are in its map path, the status of the rover itself. So all that data needs to be uplinked now back to the ISS. And we've got here our the rover sensors itself, which is the main stuff I was talking about here, and we're getting about 600 kilobits on the uplink there, and we're getting 600 kilobits on the science data. Any questions about anything? All right, this is Chris Cassidy. So this was our first crew session. So this shows Chris Cassidy in the ISS with the laptop, and we've uploaded our GUI interface. This is the GUI interface that he's interacting with, and part of our team was developed quite a bit onto the learning aspect of this. It seems to be an on-site learning experience, meaning the astronaut gets on. They got projects every day that they have to go execute. On this day, they woke up and they're told that they have to execute this robot operation. We get 3.5 hours with them for each crew session. In that 3.5 hours of the crew session, we need to include the training time. Given they've never seen the interface, they've never visually seen the robot itself or the landscape that it's driving on. So it's kind of interesting to think of that scenario where you have no actual physical relationship to this at all, right? It's a completely different aspect of it. And so we got to go through a learning phase with them, and they need to execute the mission, and then we want to get all the feedback we can out of it. So we're very crunched on time and how to make the different parts of that very efficient. Really felt that we did that really well. So Chris Cassidy was the first crew session. And so let me talk a bit about the interface here. So this is the GUI that we uploaded to the ISS. And what you see is they have a 2-page manual to learn how to use it, and then they just got to go and do the missions that we tell them to execute. So I'm going to kind of run through about what we provide for them to have situational awareness, how they know where they are on Earth. So you have a task sequence set here. So this allows us to have high-level tasks that are pre-planned during the pre-planning phase of the robot. So every row here is a different task. This one's drive to station 00. This one's deploy and drive, and we have different a set of tasks here. So in a perfect world, they would pre-plan a set of tasks that would be uploaded here. They'd click the play button, and it would kind of be watching like a virtual robot, go through its paces on here. So you have the rover in your main. We call this the bird's eye view. So this is the K10. It's wherever it's driving. The landscape that we provide for them is done off a depth image map. and we have different color codes, right? So red's an obstacle that we don't want to drive over. We have orange, that's something that it can drive over. And the astronaut doesn't need to concern himself with stopping the rover for a red spot, right? The rover won't drive over something it knows it can't drive over. So, but it provides an astronaut with a sense of the environment. And if you can see the cones here, these different cones are the different waypoints that we have set on the task sequence. So in this console setup, everything is an observation in the astronaut's point of view, except for these 3 buttons: play, pause, and skip a step. Right? Everything else is an observation. You see what task sequence he's in. You get a viewpoint of the bird's eye view. You get a top-down view, and this is a HazCam image that's uploaded periodically every time the HazCam takes an image to give them an actual viewpoint. Up on the top, we have rover status. So these are the different subsystems on the robot, and if one of them fails, it comes up in the light. We use that in our case to actually inject faults into the system to see how the astronaut would get aware of these issues and see how well, I guess you'd call situational awareness of this interface itself was. And should they come into an issue where the teleoperation pre-planned steps fail for some reason, the robot gets stuck in an obstacle scenario where it doesn't know how to get out of, or you've requested a task sequence that it didn't execute properly. For example, if we ask the robot, we pre-planned a robot to go into this position and take a panoramic camera, and the astronaut inspects it, and then it's the wrong position, we need to rotate the rover. So there needs to be a way for them to provide the teleoperation, right? So this is the teleoperation panel. So on the top left, you see the Run Task Sequence tab, and the next one's teleoperate. So with this one, they have a very primitive set of commands that they can execute. So you have some forward commands with distances, backwards, rotate left, rotate right. Panoramic and inspections, or commanding the cameras to take pictures. So while we are teleoperating, we have the low latency of a half a second. There's still this delay that we need to account for. So you can't have a live joystick driving the robot. So where do we break that up? And this is how we chose to solve that. Any questions about the interface? Why we chose certain things? Yeah.
Yeah, is this kind of a super streamlined version of what we're doing on Mars with the robots there?
Good question. So the way we operate Curiosity is a bit different, right? So the Curiosity delaying data is about 20 minutes. So there's telerobotics is thrown out the window, right? We got to have some other plan. The way the Mars Curiosity rover works, and I wrote down some numbers so don't give you false data, even though it's not the opinion of NASA. So Curiosity rover goes, its estimated distance per day is 100 meters a day, right? That's on a good day. They say majority is less, and a few times I've gone over. But the way the Curiosity rover works is it goes through at the beginning of a Mars day, we set up a plan for its entire day. And its goal is to execute those plans. The next day, we should get data back from the rover, and then we should plan the next set of steps, and it executes the next step. So it's a day-by-day controlling, right? So it doesn't fall in the definition that we've made for telerobotics. Just a bit about the Mars rover, because it was kind of interesting. But the way the Mars rover works is in its obstacle avoidance. I mean, given it has to use all rad-hard equipment, right? All the processors and everything are very limited to what we're used to, right? Even the furry guy. So the way it works is the Mars rover will drive about a foot in 10 seconds, and this is along its path or whatever trajectory we've given for its day of task. So it goes about a foot, and it'll stop there for 40 to 50 seconds, analyze its area, its map, and it keeps a map in its head of its environment of 10 meter by 10 meter around him or her. And so it analyzes it, takes 40, 50 seconds for that, then it moves another foot or so in about 10 seconds. So it's a very slow, iterative, careful, I mean, for a good reason.
But it's not actually waiting for permission from Earth before going on to the next step in this process.
Right, it's given its task at the beginning of the day to go execute it.
And so it just goes through the whole thing unless it detects some error.
Right. If it gets to some, I'm sure they have different decision chart of some sort where, or if it gets in something where it can't make a decision, you get back the next day and your status is you only complete the first foot or whatever it may be. Yeah.
How are you able to set waypoints without a GPS screw?
Right. So most planetary missions we have, we've always send out satellites prior to observe some planetary surface, right? And we have a fairly, I don't want to call it dense, but a fairly decent map of the area that we plan to traverse along, right? So we have a pre-done map of the area, the DEM of the area. And when we have the rover on there, what it's doing is it's looking at this sparse map that we have from satellite imagery, and then it's building a dense map from its onboard sensors, right? Its camera, its LiDAR, its IMU, and creating a local map for itself. And it's kind of aligning that with what it sees from DEM. So given that, and given that we have a good localization of the rover, which is one of our important services, right? It needs to know where it's at, where it's aiming, and how it's doing it. Then we can lay out the waypoints.
Would there be any virtue into having the rover use periodic contacts with the few satellites in orbit around Mars as sort of a poor man's GPS or something? Assuming you know what the orbits of those satellites are?
Restate the question, see if I follow. So you're saying we have a rover on the Mars planet, we have satellites in orbit, and we want the satellite to observe the robot and give us feedback of where it is?
Oh, no, I'm just saying is that if you know what the parameters of the orbit are,
right,
then it might be possible to use radio contacts or beacons from the orbiters as sort of a low-quality GPS.
Sure. I mean, if we have a low-count constellation of satellites among the planet, then I'm sure that's possible to have some.
Well, I think you've only got about 3 at the moment.
Right. So yeah.
So it's sort of like you're not going to get funding to put 66 of them.
Yeah. You need a spherical intersection to get those, but it's not to say that can be something that when you feed into the filter or some other with some confidence rate.
Right.
Yeah, sure.
So in your previous slide where you were showing the waypoints they were supposed to follow, is that all relative to the starting position?
Yes.
So
Yeah.
It's not an absolute coordinate, it's relative to where the robot started from.
So there's 2 ways to do this. There's ways to do it where I want to set up a waypoint and I want the rover to go 10 meters up and 30 meters over, and I want to plot waypoints along those lines. That's a fully relative path. That's fine. There's another one where I want the rover to traverse from here to here, right? And I don't know where the rover is. So its first task is to get to the first waypoint. And that first waypoint that you said is a global waypoint, right? So I want it to start at location, 3-5, right? And so in that case, the rover it's not relative to the rover. The rover needs to find that waypoint. So what I'm getting at is here you see the waypoints are kind of lined up directly in front of the rover in a straight line. It could be the case that the first waypoint was here, right? The rover started off over here. And the rover had to use its onboard autonomy and onboard localization and mapping techniques to find that first waypoint. So there's 2. You can have a fully global or you can have a relative.
By visual artifacts of what it knows is there?
Right, by stereo vision and using the LiDAR on board and building a map. Yeah.
So, as you said, most of the stuff on the Mars rover has to be wrapped hard, etc., etc. And here you show a sophisticated system where you have a camera actually video.
Yeah.
Is it that you, with so much less delay, you no longer have to comply with all these hard standards, holding standards, etc., etc.?
So there's some work being done, which is part of our future bridging gaps in this technology is can we offload some of the processing power onto the spacecraft itself, right? So it doesn't have to be done directly on the rover. And that's something we haven't dove into, but if you know, that's the next step.
Doesn't the spacecraft in orbit have to be rad hard as well? I mean, it doesn't have any more protection against radiation than the rover on the surface does.
It doesn't, but there's a difference. We have a better capability to put higher processing power on a non-landing unit.
Okay.
I have a second question. So, what's the deal with Mars rover? What's the bandwidth with the Mars rover?
The bandwidth, did I get that? I did not write that down, and I have no knowledge to be estimated. So.
Okay. I was just curious, can you explain a little bit what happens within the 10 seconds, 1 foot distance that is traveled? What is it?
So in that 10 seconds, at that point, before it starts to traverse for 10 seconds, it's now built a very dense map around it. So if it sees a rock that's not traversable or some other items that it wants to work around, it can move around that for a foot, right? Or it could be great that the path of plan is clear and it moves that foot.
So it's not doing anything special, just trying to find its way to the next way.
Yeah, we're talking about the Mars rover, the Curiosity. We're not talking about K10, about this rover.
Okay, I actually see.
So on this one, we don't have that limitation. I hope I made that clear. The drive for a foot in 10 seconds and compute for 40 seconds, that's the Curiosity rover.
Okay.
Right? This rover is completely different from that. We can give it a waypoint of 10 meters out, and it'll attempt to drive those 10 meters at the speed that we've set. Currently, we're moving at 90 centimeters a second, so just a decent walking pace, slow walking pace. Right. It's 9:40. What time do you guys want me to wrap up?
Another 15 minutes or so.
Sounds good. Go. So this is just a picture of us showing. I enjoy the questions. That's the fun part of giving these things. So this is just a picture showing our Marscape again. I'm sorry. This is Roverscape. We used to have an old kind of player called Marscape, but Google paved it over to get to the new facility. but they did help fund this one, so no complaints. This is interaction of Luca Parmitano. It's slow, but you can see it interacting with the rover. You can see the rover play back on the screen. It's moving around. It's building a map as it's driving along. And Luca Parmitano is at this point just viewing, in a supervisory mode how the robot's doing. And you can see here he's on the the task sequence GUI. So he only has the play, stop, and skip button for him to interact with.
It looked like he was doing a rotation there for viewing or for object avoidance, or what's going on right now.
Yeah, so right now the rover is actually doing obstacle avoidance. If you see kind of the red spots where the rover's kind of near, the rover's turning around and analyzing its different possible paths that it can take to work around this obstacle. And you see it found a path, and it's going to kind of go up and hopefully not run into that. Yeah, so.
Just like the back.
So this video is kind of long, but I just want to kind of show you guys what type of interaction we're getting with it, and take into consideration everything he sees here, is about a half second or so delayed from what's happening on Earth.
That image is coming from the LiDAR?
This image is a trap map developed from the combination of the LiDAR and Sierra cameras. Yeah.
What total distances are you expecting this to operate at, or what are you designing it for?
So in this one here, in each mission, I think we did about 250 to 300 kilometers per phase.
What power is it?
Sorry, not kilometers, meters.
Okay.
It's a long way. And Sorry.
What powers it?
So this rover itself has, let's see here. Each rocker on the rover, which you'll see in another picture, has a series of batteries. And they're actually, in this rover itself, they're just laptop batteries. So they're just a ton of laptop batteries. The reason we chose that, it's easy to ship. There's different regulations on battery power and all this stuff. So when you go to field tests and stuff, it was easy to ship that long. Luca Parmitano, his job was the second phase. So his job was to deploy the antenna in the rover's gate. So this is just a picture of the antenna being deployed. It's a polyimide antenna. So the rover has a little roller. When that's executed, it drops the roll and then starts driving along to extract the roll from the rover. Since it's here on Earth, we had to have a human go behind it and lay some wind barriers on top of the antenna, which wouldn't be the case on the lunar surface. But this is another video of Luca Parmitano controlling the rover. So I'll skip. You guys can, if you Google K10 and ISS, and you can run across a lot of videos on YouTube. So this is the antenna array that we laid out. So Luca Parmitano had to lay out 3 antennas. So during the site survey, they found 3 areas that were clear and free of debris, free of rocks, and we could do a straight traverse on and lay this antenna out. So this is an image of part of the 3 antennas. There, and there. And this is the interaction with mission control. So we had a lot of interaction with mission control. So this is possible because ISS and mission control are relatively close in this mission. As we get farther out in deep space, mission control is going to be farther out separated. But the goal is to figure out what type of information do we want from the ground itself to give to the rover. And how can we figure out what's important and what's not. And this would get to the point if we had something in orbit. You know, what are the critical things we want to send out when that halo goes outside the blocking viewpoint of the moon? Karen Nyberg was our 3rd astronaut to control the rover, and her job was to go back and inspect these laid out antennas. And actually, this here is her wedding band. I was on the necklace, and it was just floating around. So this is the rover now. Now the rover's job is to follow the waypoints and drive to a waypoint that we've preset during the planning phase and go and take a panoramic picture of the antenna. And here again we injected false, essentially, waypoints, so the robot was pointing in the wrong direction, and the astronaut had to go to teleoperating mode to rotate the rover and take a proper image. So we risk kind of us looking stupid because the astronaut's like, why is the rover always pointing in the wrong direction? Metrics. These are the different metrics we wanted to take in. We just submitted the paper to ICERIS if you guys want to read about it. I wasn't too involved with it, but it is interesting of how much work we've actually, some people have put into it. Different, actually developed professional processes there are to analyze these things. So future work, what I want to dive into is a little bit about our robot itself. Future work is to extend the capabilities of the rover basically on the surface. So we're laying out an antenna that's kind of just rolls out. We want to have some way to assemble the actual units on the antenna and give the astronaut more control over the rover. If we were to do an actual lunar farside mission or a Mars mission, we could expect more training time with an astronaut, so we can have more capabilities. So these are things that we can expand off of. Multi-robots, have multiple robots in the field, and having them work, cooperatively with each other. Do you have a question yet?
Yeah. How do you test for reduced gravity in robots?
I lift it. We don't. So our job, what we do here at Ames is we're a software research group. So we're developing the software technologies to deal with, to bridge this technology gap and pave the way for the next steps in these missions. the gravity side of it itself would come into more on the mechanical aspects of the rover, which that's not our strong point here.
So what was the most you learned from actually interacting with the astronauts? Did you learn what you needed to change about the software and about the training and about the dynamic coding? And
so yeah, we got a lot of feedback from them. A lot of the feedback that we got was actually due to the fact that we were injecting errors and it wasn't to what they expected. So we were injecting errors on battery level dropping, right? If we're on the lunar far side and you're going into a cave that's in pure darkness and your battery level drops, you want to get back out before you just die in there. But their complaint was they couldn't develop a model of how the battery would decay over time because it was just dropping. So those were some of the interactions. We had really good feedback on the GUI itself. So we had these three different astronauts that were supposedly independently learn our software, right? And some of them would read the manual more than the others, and you could see, we wanted to see how that affected, how can how many of us actually read a manual, and where do you find that at? So we developed a kind of a cheat chart, of different icons that we have on the GUI. So if they don't read the manual, they can maybe perhaps reference it. One thing we wanted to develop was trust in the human for the level of autonomy the robot has. Right. So when the human sees the robot going along its path, and maybe from the environment that we've given it, it knows that there's an obstacle there, but it doesn't see the robot turn. Right. So I found myself when I was testing it the first time was, my instinct is to stop the rover, right? And I know what software is on there. I'm still like, I should stop it, right? But these are things that we see them be a lot more, free with. And maybe that's the case because they don't have a physical relationship to the rover, right? It's all at this aspect. It's like playing a video game, and it really is, right? You don't maybe you don't actually have a realization that this is a rational, real, metal object that ran into a Earth rock. Right?
it's not their robot.
And it's not the robot, yeah.
Have you done any tests on kids playing this?
No, but I did realize when I went to the block party, we had a lot of kids come up, and there's some smart kids out there asking really good questions, and they lead up all their questions to, can I drop the rover next? And I have to tell them no, and they're all pissed off. All right, I got 3 minutes. So this is the K10.
2 more minutes, don't worry about it.
All right, cool. So this is the K10. I just wanted to kind of tell you guys what kind of sensors we're using on it. So kind of go from the top down. We have a Velodyne LiDAR. It's the 32 cheap version. And we have two, they're Allied Vision cameras, and we use those as our serial cameras. On the back side of that, we have the top GPS sensor. On this, we do use a differential GPS, so our main building has a ground point for that. The two cameras you see are just commercial grade Canon G9 cameras. The back one here is at a fixed angle, and what's that for? Well, that's for the robot as it's laying out the film. It's just at a fixed angle to take pictures of the film, and as it's laying it out, and upload those to the astronaut, so the astronaut can see, if the things get tangled up or needs to stop or for whatever reason. The front camera is on a pan tilt unit, so we use this to take panoramic images. So this was used for the inspection phase to go out and look at the different films, take a nice panoramic of the image. So they're separate images taken, stitched together, and sent out. That's the camera. We have a Novatel IMU unit, INS unit here, which is a really nice IMU to be able to play with. And these 4 bars that you see here are Tropos. It's a wireless mesh wireless mesh network that we use to be able to communicate and send commands to the rover from the router that we have at our base unit, basically. So any questions about the sensors we use?
Can you tell us something more about what kind of processor or computer we have on board?
So we use a Nuvo computer. It's basically it's a fanless, heat-sinked i7, i5, i7 computer to run Linux as our main operating system. So maybe that's a good segment into the software we use itself. So NASA as a community has developed a API called Rapid. It's Robot API Delegate. So this is where we set up our data structures and control segments of how to control rovers to try to have it somewhat standardized between our different locations. And in order to use that, we need middleware to communicate across these different networks. And what we've chosen is RTI's DDS, and that allows us for our publish and subscribe methods. So similar to Ross, your Ross leaders here. And that we chose that middleware because it's for our use case, it allows us a lot of fine-tuning of the quality of service of the actual messages itself. So that's paramount for us to be able to tune those elements as we deal with a very limited bandwidth network. We use Corva for our request reply to talk to the science instruments itself. And we have the overlying architecture that we use is service-oriented architecture. Service-oriented, we call it robot architecture. So there's a paper out of that as well. And we use the ACE framework for that. So we started this a while back, and we use the ACE framework. The idea is that we have individual services that we can bring up or bring down in the robot, and they can theoretically be done dynamically. So we have a localization service, a mapping service, an instrument service. This would kind of relate to a ROS node, where you can bring these up and come. And the GUIs that I've been showing you, we call that VERB. It's a virtual environment for robot virtualization exploration. It's funny, sometimes you use these acronyms, and I looked them up in case somebody asked me. But it's built on top of Eclipse. So it's an Eclipse graphical environment, and it's expanded upon to use that. So yeah, those are. So this was our old K10. We had two. We had a K10 red, K10 black, and we had them as backups during the ISS mission. And the idea was it could be hot swappable if something actually catastrophically went wrong with the rover, or it was pointless to try to fix it. We didn't actually run into that scenario per se, but we wanted to actually test the hot swap to make sure we could configure networks and everything on the fly. That's more just a testing for us as a team. So this is the new rover we have. We had an old rover that this is scaled down from that. This is a scaled version by 75%. So the old rover was called K-Rex. The new one, our formal name is K-Rex-2. So when I give you a talk on NASA's opinion, they'll have a different name for it. But the reason for us decreasing by size is the last one was too big and bulky to bring around to different field missions. This one's a nice size. It fit into a truck. We're creating a little box truck for us. It allowed us to bring it to the block party. So right now, on the left is how we brought it to the block party. It didn't have any of its avionics on board, so it was literally just like a remote controlled four-wheel steer car. And we had it was a Logitech controller controlling it. And on the right, we're integrating all of our instruments that you've seen on the K10 onto the K-Rex for our future missions. So this is just kind of showing the large capability. I mean, we always have an e-stop with the rover, so if it thinks it's going to go over something it can't handle, there's the fail-safe. It's always the e-stopper that needs to stop the rover. With the new K-Rex, it's like the definition of a rock changed. You can drive over so much more, and it's so much more capable.
That's the gelatin for you right there.
Yeah. So we're really excited to go on our field test. The upcoming field test we have in October this year is go to the Mojave field test. And what we want to do there is demonstrate with high fidelity some instruments that we want to use on the resource prospector mission. The resource prospector mission is a mission that we want to have to scout land and find volatiles. So we want to be able to, essentially they're looking for hydrogen. So we have two main instruments that are close to flight ready instruments that we're going to have on the rover. One is a neutron spectrometer, and one's a near-infrared camera to scout the ground in front of us and map out the area. And we're going to do it in the Mojave Desert, and the cloud or the Earth science team here, we're going to try to classify what type of cloud cover on the desert, relates to different types of hydrogen values underneath. And this rover itself splits up, so the two rockers come apart fairly easy. There's a passive link between the rocker and the main body. If you take those apart, the rockers pop off, and the main body has the actual batteries inside it. They're the size of 3-car batteries. And the idea with this rover is to never pull the batteries out. I mean, we have about a full day of continuous driving or power on board the rover itself. Yeah.
So you're saying you guys are on the software side and Eames. Who designs and builds your hardware?
So this rover was built by Proto Innovations, which is headed by a faculty member from Carnegie Mellon. I guess spun off this company. And Proto Innovations is the same company that built the K10s for us as well.
And are these dedicated design specifically for your work, or are they being used by other groups in NASA?
They're primarily designed for us. I know they've had copies that CMU has used, so some of the requirements have been a joint requirement collaboration between CMU and Ames. Yeah.
So for software that you showed, can you assess how complex the rover side software is? What's the order of magnitude? How many lines of code is running on the rover?
That's a good question. I don't know. There's a lot of to go.
Yeah.
I don't have a number for you. It's one of the longest running software projects in the group.
So how big is the group, and how long would it take to actually get to the stage where you can see now?
Sure. So the IRD as a whole, we're about 30 strong, but they're different groups. Some work on spheres, some work on mapping, and there's a group called Consecutive Robots. The rover team itself, we vary. So since I've started, it's been close to about 4 and gone up to 8, and I guess kind of in that range itself.
So when you guys write software, is it actually according to all the coding standards that you have used on the target mission?
So we don't develop flight software. If that's your question. We have coding standards that we abide by as a team. They're not flight software coding standards. So what the idea is to develop the technology here, bridge the gap of technology, and descendants of this technology will be further refactored and whatnot into a flight ready system.
You mentioned this API Rapid.
Rapid, yeah. Robot.
Where does that fit into all? Is that something you wrote, or is that something that you got code from some other part of NASA or something?
That's something that different NASA communities, JPL and Ames and JSC, have collaborated together to try to develop an API that we all
So is it just an API that you have as a standard, or is it actually a pile of software that implements that API that you pass around?
So formally, I believe it's just an API.
I see.
On the robot side, it's very closely tied to DDS for passing the messages back and forth.
Okay.
I know different teams that will use a different version of DDS. So I believe the answer would be it's formally strictly a data structure. That
An interface.
Yeah, and basically an IDL.
Yeah.
Yeah. These are acknowledgments of lots of different people that were involved in the telerobotics mission we had at ISS. And I guess I can close.
Yeah.
Happy to answer any more questions.
Further questions, everybody? you've had a lot of questions have been going on concurrently. So, Alan back there?
Yeah.
So you talked about some of the navigation techniques to avoid obstacles and so forth. You also use optimization for power, navigating to waypoints to minimize power usage?
No, power is not a metric that we put into our pathfinding techniques.
Is that a possibility? Because that is one of the limited resources on those is now.
Sure, it's definitely a possibility to put it to the pathfinding itself. Yeah, there's for this mission itself, pathfinding was a lower priority task. We want to have a localized pathfinding to go around local obstacles. We're not even running a global pathfinding algorithm on here. It wasn't a priority for this task, but that could definitely be an objective to put on the pathfinding algorithm.
Are there any further questions? Okay. In that case, I'll ask one question. Do you know how much approximately the K-10 costs? I realize this is government stuff and it'll fund money, but...
Sure. Well, since I'm not reflecting any opinions, the K-10 was done before I started, so we had that rover ready. The K-Rex that you see is about 100K, from my understanding. Yeah.
Okay, I'd like to thank our speaker. Follow-up questions up here afterwards.
Yeah.
And be sure that, I think, where is it? Here it is over there. The autism robot is over there. So if you have further questions about that, I'm sure the autism team will. I'm spacing on the name of the robot. See, Maui or something? Robimo. The Robimo team, I'm sure will give now tongue twisted. We'll be delighted to answer questions there. So with that, what we'll do here is we will wrap up, okay, from now until about 10 o'clock. We just wander around and talk with one another. And at about 5 to 10, I start kicking people out to the parking lot. And some of us, we just can't let go. So we'll stand out in the parking lot and talk until Google security comes around and kicks us out. Okay, thank you very much for coming. We hope to see you next time.